Anybody listening early, folks, just to let you know that the Hangout will start in about 5 minutes. So well done if anyone's already tuned in and set up and good to go. So about 4 or 5 minutes, get yourself a cup of tea and a nice cup drink or something. Right, ladies and gentlemen, let's go live then. Thank you very much for tuning in to the night before the exam, Physics Paper 1 Revision Hangout. Going to try and capitalise on a few key things this afternoon in preparation for your exam tomorrow. Hopefully you've been having a look at the key reminders here. Hopefully from all your exams, I shouldn't need to say these things, but get a good night's sleep, eat a really good breakfast, make sure you've got the right equipment for the morning. And now for this physics paper, please make sure that you and all your friends know you're going to need a protractor. Okay, so first thing tomorrow, if you don't have a protractor tomorrow morning, come and see your science teacher, and make sure you got one, because we've just recently found out that they're now going to be needed in the paper, potentially needed in the paper for you to measure an angle. So let's get started then. Tonight I'm hoping to go through some of the required practicals. So there are 4 required practicals for this physics paper, 3 if you're on combined, and one extra if you're doing the separate sciences, this one here for the separate science. So let's go through some of these, then I'm going to pick out some of my top tips for what's going to come up in the paper, key things to make sure you're familiar with as we go in. And I'm going to try and go a little bit slower today than I might do in some of my previous Hangouts. So do just give me a shout on the wall on Frog. If I'm going too quickly, just say so, slow down, take your time. And if you've got any questions as well, feel free to write those on the wall. Okay, so the first required practical, one of the first ones we do at the end of year 9, is to calculate the density of objects, to find the density. Now, if you're going to be calculating the density, you've got to be using this equation here. Density equals mass over volume, because density is the amount of mass you can fit in a particular volume. So density equals mass divided by volume. If you're going to be doing a practical to find out the density of things, you've got to be weighing the mass. So you're going to weigh mass by using a pair of scales. So every practical to do with calculating density, you're going to have to weigh things on some scales. Okay, let's start with a cuboid shape. So that's something that could be a cube or a kind of rectangular shape. Okay, well, if you're going to be using this equation, you're going to weigh the mass of this cuboid up on the scales up here. You're then going to work out the volume. Now, volume for a cuboid is going to be its width times its length times its height. And that's why it's going to give us our volume there in meters cubed, because it's our length times the length times the length, so meters cubed. Okay, so that's for cuboids. You weigh it and work out the volume. Now for liquids, any liquid you can put into a measuring cylinder. And when you put it into a measuring cylinder, the reading in milliliters off the side there is exactly the same as your centimeters cubed. So 1 milliliter equals 1 centimeter cubed. You'd want to weigh the liquid again up on the scales to give you your mass. And you know, you're going to do your mass divided by the volume from the measuring cylinder to tell you the density. Okay, now probably maybe more likely to come up might be the how to work out the density of an odd-shaped object. So by an odd-shaped object, we could mean, for example, a Lego man that we did in year 9. Don't know why his arms are coming out of his waist there. There we go. There's his proper arms. So we're going to have to work out the density of our Lego man. Just laughing at my own drawing. Work out the density of the Lego man. So we're going to pop him onto the scales to work out his mass. And then after we put him onto the scales, we know our mass. We're then going to be putting him into one of these cans here. Now this can is called a Eureka can or a displacement can. Now what you're going to do is you're going to place, you can see that the water fills right up to the very top of the can there. And then we've got a little spout out the side. And this little spout, when you put your Lego man or your odd-shaped object into the Eureka can, he's going to push water out and water's going to come out of here. The exact volume of the water that comes out is the exact volume of the man that you put in. So that measuring cylinder there will then read off, you'll be able to read off your volume of your Lego man. And you do your density divided by volume. Now take care if your mass is in grams and your volume is in, for example, centimeters cubed, well then your density is going to be grams per centimeter cubed. So just check your units and that you're using the ones that they want you to in the question. Okay, so required practical number 1, done. Okay, next one then. So this next set of required practicals is all based around resistance and using this lovely equation up here, V equals IR, or VIR. So V equals I times R. V being potential difference, I being current, and resistance, R being resistance. So the basics of these, this part I've shown you here is just how to find the resistance of a component. Now this isn't in itself isn't a required practical, but the science here is really useful in the practicals I'm about to show you. So if you want to work out the resistance of some mystery component, here's my mystery component here, okay, a resistor. If I want to work out the resistance of that, I'm going to need to do, I need to rearrange the equation. So I'm going to rearrange V equals I times R to R equals V divided by I. And I'll show us later about some skills for rearranging equations. So I'm going to rearrange that equation. Now I've got to make sure that I place my ammeter to measure the current, to find that I there. I've got to place that ammeter in series. And I've got to place my voltmeter in parallel. And you've got to use those words series and parallel to describe it accurately. Okay, and once I've put my ammeter in series and my voltmeter in parallel, I then rearrange this equation to find the resistance. Now, in the first of the required practicals, you're expected to show find out how voltage affects current in a component. So if you're going to look at how changing the voltage affects the current, you're going to need one of these. This here is a variable resistor. That allows me, because I can vary the resistance of it, I can increase or decrease the resistance, which will in turn increase or decrease the current and increase or decrease the voltage. So if asked to show how voltage and current are related for a component, for example, a bulb, a diode, or a resistor, you can use the variable resistor to change the voltage while measuring the current and the voltage through the component. So you may also be expected to plot a graph of this. And there are three components you might be expected to do this for, either a bulb or a diode or a resistor. Okay, now if this is your practical, there are some variables, just like any other practical. So the independent variable for finding how voltage affects current, I would be changing the potential difference of voltage. dV, we'd be measuring the current going through it. And the CV, control variable, would be keeping the same component of the same resistance, and the length of the wires, possibly. The length of the wires sometimes affects it. Okay, so the three components that you might be expected to do this, how current affects voltage, are these graphs here, which you will have seen before. So for my resistor, here's my resistor there, that rectangle. A resistor at a constant temperature has a directly proportional relationship, meaning that it's a straight line and goes through 0, 0. Now my bulb, which is down here, my circle with a cross in it, my bulb has a graph that is this shape here. Now a bulb heats up, which is why when it's really hot and it's got a lot of current flowing through it, it's got a really high resistance, which is what makes it light up. And here's my diode. Well, the job of the diode is to only let electricity through one way. Okay, and so we can see that that is exactly what this graph is doing. When the current flows in the negative direction, there is no current whatsoever. When the voltage is in the negative direction, there's no current. And when the voltage is in the correct direction, well, there is a current flowing. So the job of this, just like the shape of the symbol shows us, is to control the flow, the direction of current. Okay, more required practicals involving circuits then. So if we wanted to look at the effect of adding some resistors in series, we're going to need to still be using our same equation, V equals IR. We're going to be adding some of these resistors in series. So add the resistors in series, record the voltage across the resistors and the current around the circuit. You're going to use R equals V over I to find the total resistance. We would find that the resistance of the resistors adds up when added in series. So when we look at a graph of that, as we add our resistors in series, and just make sure that your voltmeter goes right round all of the resistors there, because it's the total resistance that we're looking at, we would find that that would be directly proportional, that the more resistors I add, the more the resistance is. Okay, adding them in parallel now. So here's my circuit again, my ammeter, my voltmeter still in the same place. As I now add my resistors in parallel, and again making sure my voltmeter goes all the way around the outside, we would find that the total resistance of the resistors gets less when added in parallel. And so if the resistance is getting less as I add more resistors, we would see that as I add more resistors, the resistance is going down. The graph would be roughly this shape. Okay, our third required practical for combined scientists. This is the specific heat capacity required practical. And I think my gut feeling would be, if they're of the three, this is one of the more likely to come up. So if this is about finding the specific heat capacity for a material, we need to know what the definition of specific heat capacity is. So if the specific heat capacity of a material decides how much energy it takes to increase the temperature of 1 kilogram mass of material by 1 degree Celsius. Okay, now we have an equation for this, but the good news is you do not need to learn this equation. You get given this equation on the equation sheet. You also get told what the things mean, and we're going to have a little look later how we pick out equations off the equation sheet. So my tips are, use the equation given on the equation sheet. If this is your required practical and you're asked to make a method for it, use the equation on the equation sheet. Now, another tip is that they like to leave off any insulation off of the block, and the metal block should be insulated to prevent heat loss. Okay, so let's just say that they asked you to write a method on how to find out the specific heat capacity of an aluminium block. Okay, well, the first thing is our job has to be, if we want to find that, let me just get rid of that. If we want to find our specific heat capacity, C, well, then we need to have a method that allows us to find theta, the change in temperature. We have to write in our method how we're going to find M, the mass. We have to write in the method how we're going to find E, the amount of energy given to the block. Okay, so the starting basis of our method is the equation, and our job in the method is to say where we're going to find these missing values from. Okay, now this is the simple version of this. They may ask you to do a diagram as well, and I'll just explain the diagram in just a moment. So the first thing that they're going to need you to do in this method is you've got to say where we're going to find M from. So M is the mass of the block. You would put them onto some scales. Then you've got to make sure that the block is insulated. So we're going to have a nice kind of layer of insulation on the outside of the block there. That's so that the energy you're putting into the block stays in the block and increases the temperature. You're going to turn on the heater for some amount of time, and you've got to find a way, some mention about how you're going to record the energy transferred to the block, our E there. Now in this example, I say we use a joule meter. It might be enough for you in the exam to get full marks, but the AQA exam board have told us of a different way that I'm going to show us in just a second. So if in doubt, if you're worried about learning all of the steps, just say we're going to use a joule meter. We'll record the energy going into the block. Okay, then we're going to turn off the heater after a certain amount of time, and we're going to write down the final temperature. This will let us work out the change in temperature, our theta. So look, as I've gone through the method, there's my mass, there's my energy, there's my theta. I am now telling them the things in the equation. Final step, rearrange the equation. Now you would, if you're worried about rearranging the equation, just say use this equation here to find C. You'll still get marks for all of the other things you've got. So that could well get you maybe 4 out of 6 marks in quite a difficult required practical there if they ask you for the method. So for the diagram here, you've got to make sure if they ask you to draw it, you've got to make sure you've got an aluminium block. This here, a thermometer for taking the temperature. This here is the heater. Okay, and from the heater, there we've got our power pack powering the heater. Okay, a slightly more complicated version, but the complete version now will be the same principle of us using our equation here of E equals M times C times theta. But this time we're going to use a slightly different method for working out the energy transferred to it. Okay, so again, we're going to start off by measuring the mass of the block M on some scales. We're going to insulate block and take the starting temperature. We're going to turn the heater on, but this time we're going to time how long the heater is on for. That's going to give us T. We're going to use an ammeter. So the ammeter has to be in series with the heater. You see it's all on a big loop here. Here's our power pack. The ammeter is in series with the heater, goes back to the start. Our voltmeter is in parallel to the heater. So it's coming off of either side of the heater there. So we're going to use the ammeter reading, I, and the voltmeter reading, V, to then use this equation, P equals I times V, to find the power of the heater. So we're going to know T, we're also going to know P. We can then use, because we know T and we know P, we can then calculate the energy transferred to the block. So the energy transferred to the block would be your time taken for the heater that the heater's on for, and the power of the heater that you've worked out from I times V. This will tell you E up here. So we know E, we'll know M. Now we'll take the final temperature after the time is up. That's going to give us our change in theta there. So you can see, really similar method, but this one just includes a couple of equations on how we find E, the energy transferred to the block. The previous method just kind of blended those two bits into one and just said we use a joule meter. But this one will give you the full marks if you can remember this one. Okay, now this one is a separate science only required practical. It's only a short one, so I'm just going to go through this quickly, and bear with me if you're a combined student. This lesson could still get taught to a combined student, so it is possible that they may bring this this practical up in the combined paper, but it's not one that we expect them to bring up. So this is comparing the rate of heat loss of different insulating materials, as in how quickly heat comes through it. So you would get a large container, you'd fill it with your hot water, and you would put round the outside the insulating material of your choice. And you could have different jars for each different material. Of course, having one without any material on the outside to act as a control that we can compare our results to. So we're going to place the different insulating materials around a container with hot water in it. Take the starting temperature, take the temperature every 30 seconds. And this is going to give us a lovely graph of the temperature falling, and we're going to be able to see how quickly the temperature falls at different times. Now, where does the temperature fall the quickest? The temperature falls the quickest at the start, and there is a bigger temperature difference between the water and the outside. So the bigger the temperature difference, the quicker the temperature will come down. And that's why towards the end of heating, it's just going to curve off, because as it gets closer and closer to room temperature, it loses less heat each minute. Okay, so those are our required practicals that we've gone through there fairly quickly in those 4 required practicals. Now, I wanted to spend a bit of time just picking out some math skills, as there is such a large proportion of the physics paper does use equations. So you can see here I want to go through selecting some equations, recalling units, how to convert units, rearranging equations using sig figs and decimal places. So we've got to start with recalling some of the paper 1 equations. Now I'm going to show them all to you, but there will of course be some that I think are possibly more important than others. But obviously at this late stage, the more you can learn, the better. So the first one is pressure equals force divided by area. So this is to do with the force of particles hitting a surface. So if I've got a balloon or a car tire or a bicycle tire, the force of those particles hitting the inside of the wall divided by the area of that surface. So the bigger the area, the smaller the pressure, and the bigger the force, the bigger the pressure. Okay, then we've got our 2 energy equations. Now, just teaching these this morning to my year 9s makes me realise how important it is that we teach them well and that we get you to learn them right from the start. So kinetic energy is a half mv squared. And you really want to be able to make that fly off the tongue. So half mv squared. And the more quickly you say it to yourself and the more passion you put into it, the more you remember it. So kinetic energy is a half mv squared. Now, just to remind you that the v squared, the squared only applies to the v. Okay, the squared does not apply to the m or the half. So you're just going to square that v there. Gravitational potential energy, it's m, the mass of it, times the gravity strength times the height. Okay, so potential energy is mgh. Okay, 2 more equations here. So power. Power is how quickly you do work. So power is work divided by time. It is also energy transferred over time. So P equals E over T, P equals W over T, and that's because energy transferred to a substance is the work done on it. So work done and energy are literally the same thing, just with different words. Okay, now if we want to know the efficiency of a machine, the efficiency of a machine will be the amount of energy that comes out of it. Let me just highlight some of these. So the amount of energy that comes out divided by the total energy you put in. Doesn't really help me highlighting it like that, does it? Here we go. It's the total energy, the useful energy that comes out of it over the total energy you put in. So in any machine, you're going to be putting in a certain amount of energy, 100 joules, let's say. Let's say it's a TV, and out of light and sound, we get 80 joules of light and sound that comes out of it. Well, then our efficiency would be our 80, our useful energy out, divided by our 100. And as a ratio, that would give us a 0.8. Now, if we wanted to turn that into a percentage, all you have to do, times by 100, and that gives us 80%. Now, energy being transferred out of a machine, it works exactly the same with power. So the useful power out of a machine divided by the total power that goes into a machine. Now, we need to know units for these, of course we do. So after having recalled an equation in the exam, P equals F over A, E equals a half mv squared, EP equals mgh, P equals E over T, P equals W over T, we need to know the units for these. So pressure is measured in pascals, force is measured in newtons, area is m squared, meters squared, work done is joules, and because energy transferred is joules as well, it's the same thing, same units. Power, people will laugh when I say power with my classes, but that's how I call it now so that you know the units. W, watts, so power is measured in watts. Mass is measured in kilograms. Now, why have I put a kilo in a red there? It's because kilo is a prefix for all other units. But for mass, mass is actually measured in kilograms. That is the SI unit for mass. Just like the SI unit for power is watts, and the SI unit for energy is joules, the SI unit, that's the standard international unit for mass, is kilograms. So if you see an answer in grams, you've got to turn it into kilograms. Okay, so all the other ones, if you were to see kilojoules, you would turn that into joules. But for mass, mass is supposed to be in kilograms. Okay, some of the other units then, we've got height in meters, and those will be our units. So recalling other equations now. These ones are mostly the electricity ones, and we can see our density equation down there again. So with electricity, kit, Q equals IT, charge equals current times time. So it's well worth remembering that current sometimes has the symbol I, well not sometimes, does have the symbol I. Charge flow has the symbol Q. So kit, Q equals IT. V, voltage, equals current times resistance. So kit, V. This one I refer to these two, swap these two rounds. We've got PIV. So PIV being power equals current, I, times voltage, V. So PIV. And then this one here, P equals I squared R. That's us really relating, combining these two equations here into power equals current squared resistance. Now, EPT, E equals P times T, energy equals power times time, and E equals QV. Now, I see that one probably the least out of them all, E equals Q times V. The one that we see the most out of all of these is definitely V equals IR. We've already seen it 2 or 3 times in our required practicals. That their density equals mass divided by volume is another one that comes up in the required practical, so a really important one to learn. Okay, our units then for some of these things. So charge is measured in coulombs. Some people think of that as maybe Columbus when they're learning it. Charge in coulombs. Current is measured in amps. That's why it's called an ammeter, because it measures amps. Potential difference is volts. V. Resistance is ohms. Power is watts, we've had that one before. Energy, joules. Mass, kilograms. Density, now this one, I like these ones because you can work this out from the equation. So density is kilograms per meters cubed, and here is mass, which is kilograms, volume, which is meters cubed. So if you know the equation, you also know the units for density as well. Okay, now selecting equations, you're going to get given a sheet with equations on. Not all of them are needed for paper 1. So I'm not going to tell you which one, you don't have to remember which ones are for paper 1 or not, because you'll only need the equations when a question tells you to go and look for them. So if we just have a quick look at these though, if you're a foundation pupil doing combined, we'll just go through the paper as soon as you get in there and cross out any with an HT next to them. HT means higher tier, so as soon as you go into the exam, you can cross out any with the HT on if you're a foundation tier paper and it's got an F on the front of your paper. Okay, so these equations here, just to remind us what they are, there's an equation for density in water, and that is h, the height of the column, times density of the liquid times the gravitational field strength. That's just higher tier only. Then we've got one for calculating the elastic energy in a spring. We use that spring constant that you would have seen somewhere else in our Hooke's law equation. That's in paper 2. And here is our required practical equation. So that's really good news if they ask you about that, because there is the equation there for that. And I remember telling someone earlier today that you needed to learn that. My mistake. You don't need to learn about a specific latent heat equation because you get given it here. And then for gases, your pressure times your volume equals a constant. So that's just to remind you of them. But of course, you don't need to learn those because you get given them. So what skill will you need when using these equations that you get given in the exam? Okay, here's a typical exam question. Energy transferred to the water is 10,050 joules. So I'm going to write E up there. And this is how I'm modeling to you that I would expect you to do it. So the time taken for the water to increase, the water temperature to increase. So that there is my increase in temperature. Now, just because I'm a physics teacher, I can remember that the temperature, change in temperature is theta there, and I know lots of you can as well. But there's T equals 5 minutes. And here my specific heat capacity is that there. Now, specific heat capacity from the equation is there. Now, you're thinking, okay, there's a couple of things we need to do here. We need to make sure if we were going to use the time, which we're not in this case, we would need to turn that into seconds. But more on that later. What we are going to have to do is make sure that we pick the right equation. So I've just deleted my writing there, but we have E, we have temperature increase, we have specific heat capacity, and it also says down here use the correct equation from the physics equation sheet. So that's my prompt to tell me I need to go and look for it. But also, let's just say I couldn't remember the equation myself. I'll go and have a look. So I'm looking for now, on the equation sheet, I'm looking for these keywords. I want to find, it could be time, it's definitely energy, temperature, specific heat capacity, and I've got to go and look for these. Now, when I scroll through my equation sheet, there's my change in energy, there's my specific heat capacity, mass, temperature change, that's the one. So I would then write down my equation, my change in energy equals mc delta theta. Okay, I would put my numbers in, and that would get me to the correct answer. Okay, let's just have a look at this example then. So this is now, we're going to have a look at converting prefixes. So this is a typical question that I've cobbled together. So at the lowest point in a jump, the energy stored by a stretched bungee cord, so a stretched bungee cord, the energy is 24.5 kilojoules. The extension of the bungee is 10 meters. Okay, the bungee cord behaves like a spring. Calculate the spring constant. Calculate, I'm going to put a box around that. Use the correct equation from the physics sheet. Okay, so good news. I can go to my physics equation sheet. I can look for something that has energy, something about it being stretched, the extension, spring constant. So looking at my equations that I've got on my sheet, I go through and I can see here elastic energy, spring constant, extension. Okay, that's my equation that I need. So I'm going to write that down. That's the first thing we need to do is just write it down. So there it is. But now there's a problem. I need to, before I can put my numbers into the equation, I've got to make sure that they're in their SI units. And can you spot which one isn't in an SI unit? Yep, my energy. So I've got to convert 24.5 kilojoules into just joules. Now I'm going to show you in a second how to convert those, but a kilo means 1,000. So I've got 24.5 thousand joules, as in 24,500 joules. So now that I've converted it, I can just put those numbers into the equation, substitute them in. There's my energy, it says 24,500. There's my 0.5, my half, times by K, my spring constant, times by the extension of the cord, 10 squared. So what you want to do now is just to do the sums that you can first. So 24,500 equals, now on this side I did 10 squared, which is 100. 100 times by 0.5 is 50. So 50k. Now, because I've got 50 in the k on its own, I've got to do the opposite to get rid of the 50. So at the minute, that's times by 50. So I've got to divide both sides by 50. So 24,500 divided by 50 gives me K, and that gives me my spring constant of 490. Okay, so let's have a look at how we can use those prefixes then to make to correct the into the standard international unit. So we've got getting bigger. To make things bigger, if we've got no prefix at all, that could be our joules, for example, or our newtons. Okay, if I've got kilonewtons, I'm making it 1,000 times bigger. Meganewtons, 1,000,000 times bigger. Giganewtons, 1,000,000,000 times bigger. Now, when we're getting smaller, if I've got my newtons here and I want to say a millinewton, then I'm dividing by 1,000. Micronewtons would be dividing by 1,000,000, and nano dividing by 1,000,000,000. So just in case you're not sure, you're not confident about what a billion and a million is, a billion, 9 zeros. Look, they go, you put little commas between each 3 sets of zeros. So that's kind of like 1,000, 1,000, 1,000. Or in standard form times 10 to the 9. Okay, mega, if I wanted to turn 3 megajoules into joules, which could be a typical exam question, I would need to do 3 times by 1,000,000, or 10 to the 6. Okay, killer is 1,000 times bigger, so 3.2 kilovolts. 3.2 times 1,000, so 3,200. Okay, now milli, making things smaller then. I'm going to divide by those same numbers because I want to make it smaller. 6.5 millijoules is going to be 6.5 divided by 1,000. If I wanted to find microamps, 3.35 microamps into amps, I'm going to divide by 1,000,000 or divide by 10 to the 6 or times by 10 to the minus 6. Okay, nano, I'm going to divide by 1,000,000,000 or times 10 to the minus 9. Okay, if we want to use some sig figs or we want to use decimal places. So here's a question, a typical question, which gives us a bit of information. So I would be underlining, I'd be highlighting my power. Actually, let's just underline those because it looks a little bit better. Here we go, power. 230 volts. Here's the equation. You may well see them giving you equations in this physics paper. Here's the equation here. Calculate the current passing through the new shower. Give your answer to 2 sig figs. So the sum here is really quite straightforward. I'm going to put in my power and divide that by the voltage there. So power divided by voltage. Those two numbers, and here is my current. So on your calculator, you'll read 46.4782606, but the question asks for it in 2 sig figs. And look how many marks there are here. There's 4 marks for doing this type of question. For writing out your equation first, putting your numbers into it, really clearly saying what sum you're going to do, writing down all the numbers off the calculator, and now putting them into 2 sig figs. So 2 significant figures means I'm rounding it to I'm only going to write down 2 numbers. Okay, so I'm only going to write down my first 2 numbers. The last number that you write down is a rounded number. Now in this case, because the last of the 2 significant figures is going to be my rounded number, I look at the number after it, it's a 4, so it's less than halfway, so I'm not going to round it up, I'm going to keep it as 46. Okay, so to 2 sig figs is 46. Now if that was 46.5, I'd be rounding it up, it would be 47. So here's an example of how this number would be turned into sig figs for 1 sig fig. Okay, so for 1 sig fig, I'm going to write down the first number, but I'm going to round it. So my 4 would turn into a 5 because my 6 is in the above 5. Okay, to 2 significant figures would just be 46, as we've seen. 3 significant figures then would become 46.5. Why? Because first 3 numbers there, 46.4, but the last one is going to get rounded. And so I look at the number after it, that's above 5, so I round up my 4 to a 5. So 46.5. Okay, so to 4 sig figs, I'd be writing down the first 4 numbers. That last one is my rounded number. I look at the number after it, is it above 5? Yes, it is, so I've got to round it up. Okay, rearranging equations then. So if we've got to rearrange an equation with 3 things in, it's easy to use an equation triangle. So what we do here is our triangle comes blank. It's already got our divides and our multiply in there. So what we've got to do is, if we can recall v equals I times r, we've got to put them into the right places. Now the symbol that is already there, that's how you place them into the right places. So if it's I times r, you know you're going to have to put your I and your r there, leaving only one space for your v at the top. Okay, if it should have been maybe a divide by sign there, you would put your I at the top. Okay, and of course, what I should say here is that when you've got your three things written into your triangle there, you cover up the thing you're looking for. So if you're looking for I, you do v divided by r. If you're looking for r, you do v divided by I. If you're looking for v, you do I times r. So you cover up the thing you're looking for, and you do what's left from top to bottom or from left to right. Okay, if we had to rearrange an equation with more than three things in it, so for example, you've done a really good job of remembering that potential energy equals mass times gravity times height. They're asking you to find the height, and they've told you the energy in it, they've told you the mass, they've told you the strength of gravity. So how do we do this? Okay, first thing to do, always write out the equation. Second thing to do, put the numbers in the right places. So potential energy, we said, was 100 down here. Mass is 5, gravity strength is 10. We've got our h there, our unknown quantity over there, with numbers next to it. So first off, do the sums you can. You've got a 5 times 10. Let's write that down as 50. Okay, now just like we did before, we've got to do the opposite to both sides. So if we want to get rid of a times by 50, we've got to divide by 50. And there we go. So 100 divided by 50, giving me a height of 2 meters. So top tips, always write down the equation, subs in your numbers, do the sums you can, do the opposite to get rid of a sign. So times by 50, you're going to divide it by 50. If it was divide by, you'd be timesing it. Okay, so that's my required practicals and my maths tips out of the way. So now just a few top tips about what I think is going to come up. Now I'm going to go through, the 4 topics for combined and separate. Then after that, I'm going to pick out just a few higher tier bits, and then for the combined, and then I'm going to pick out the separate only content at the end. Okay, so particle model then in physics. I thought I'd start us off with a few 1 mark questions here, ideas here, because I think this is something new to the topic, to the syllabus, and I think they're going to ask you about it because it's new. So key terms, a system. A system is just the object or situation you're looking at. So a system could be a falling ball, it could be a kettle full of hot water. That could be described as a system. And a closed system then, a closed system is just where no energy or matter can enter or leave. So for example, a kettle of hot water where no energy can be put in, no extra particles can be put in, or a falling ball, which is where no pieces of the ball are going to come off, and it's closed, as it were. Now, something else that they've recently introduced to this course is the idea of internal energy. So imagine you've got a kettle of hot water there. Well, the internal energy inside that kettle is made up of 2 things: the kinetic energy and the potential energy of all the particles in the system. So this will be due to the kinetic energy, just means how quickly they're moving, and the potential energy refers to like whether they're solid, liquid, or gas. So if they're a gas, they'll have lots of potential energy in them, whereas if they're a solid, they'll have less potential energy in them. Okay, so I think that those could be words that they might ask you about, maybe a 1 mark question. They might use those words in the questions too. Okay, so particle model. Now I think that this is, the fundamental of lots of the physics that we do in GCSE. So I think it would be a good idea just to be super familiar with this before tomorrow. So what I've done here is I've got a picture of solids, and you can see they're all in neat rows, and they're all vibrating. I guess that's what these little lines around the outside mean. So I thought I'd just go through a few things that you might want to say about solids when asked to describe their motion, or describing their forces of attraction, or describing their arrangement. Now notice those words that I'm using, like arrangement and motion, because those are the ones they'll use in the exam. So motion, the particles vibrate. They've got strong forces of attraction, and the particles are really close together. So the particles vibrate, they're in a regular arrangement. They're in really neat rows, and they just wobble backwards and forwards. Strong forces of attraction, well, that explains why when you put a solid into a box, it keeps a fixed shape. So if I've got a box and I place a solid object at the bottom, it stays in that shape. That's because there are strong forces of attraction between the particles. They're holding onto each other tightly. So the ones at the top stay at the top. They don't fall off. Now, the particles are really close together. They're so close together, in fact, that explains why they cannot be compressed. So if you get a solid and you apply forces to them, you can't squish a solid. And the reason why you can't squish them is there's no space in between the particles. The particles are so close together that they won't get any closer. Okay, liquids. So liquids are kind of between solids and gases. We're going to see that their motion is going to increase, their energy is going to increase, the distance between them will increase just a tiny bit, the forces of attraction will get less. But if we use some key words here, well, the particles' motion, they will flow over each other. And this explains, because they can flow over each other, this is why we say they're in an irregular arrangement. Irregular just means an odd arrangement or no pattern. So you're welcome to just say they're in no pattern. They've got weak forces of attraction. They still have some, but they're very weak. Now this explains why when you if you tried to put a liquid in a container, it would spread out to fill the whole container. Why? Because the forces are weak, so bits fall off. Okay, because they've got weak forces in there. But they're still really close together. So this explains why you cannot compress a liquid. So if you were to try and squeeze a liquid, you wouldn't be able to, because they're still really close together. Okay, now gases then, so what is their motion like? Well, they move in random directions. You can see all of these particles here would be moving in all different directions, all random directions with random speeds as well. They've got an average speed. You know, their average speed helps define their temperature. How fast they're moving gives them their temperature. So they would have an average speed, but each particle would be moving slightly faster or slower than the average. So particles move in random directions, which explains why particles are in, again, irregular arrangement. They've got no pattern. They are spread all over. And now there are no forces of attraction in this, so these particles are not attached in any way to any other particles. This explains why when you put a gas in a box, it fills the whole container, because there's no bonds between them, so they are free to move around in all directions. Now here the particles are far apart, and because they're far apart, this explains why you can squash a gas. So you can squeeze a balloon, you can squeeze a bicycle tire, because the particles are far apart. Okay, so in topic 2 is about energy, and my top tips are for transferring between energy stores. Now, it might be the case that they talk about energy stores in terms of maybe transferring energy into a kettle of water, but I think there is a strong possibility that they might talk about the energy being transferred between objects. Now, important to remember when transferring energy, energy cannot be created, it cannot be destroyed, it can only be transferred from one store to another. Each time energy is transferred, there will be some wasted energy, and usually heat, which then warms up the surrounding air. Now, if we consider the case of a car being put on top of a roller coaster, don't ask me why, this is the best pictures I could find. We're going to put a car on top of a roller coaster. Now, in order for me to lift it up, I've got to do some work on it. So the work done to lift the car is the same as the energy transferred to it. So I'm doing some work on the car to lift it up. The amount of work I do, let's say 100 joules, that will be put into its gravitational potential energy store. Why? Because I'm lifting it up. I'm doing 100 joules of energy to lift it up. When I've lifted it up, it's going to be at the top. It now has 100 joules of gravitational potential energy. Now, as the car speeds up down the ramp, there's going to be another transfer between energy stores. So work done into lifting it is going into its gravitational potential energy store. At the top, it's not really going to be moving. It's going to just maybe start to slowly speed up down the ramp. The gravitational potential energy store transfers into the kinetic energy store as it falls. So potential energy into kinetic energy as it's going down the hill. Now at the bottom of the hill, it's going to have no more gravitational potential energy. It's going to be all kinetic energy because it's moving so quickly. And at the bottom, he's going to want to put his brakes on. So that kinetic energy then is going to transfer into the thermal store in the brakes. There's going to be friction in the brakes. It's going to make them warm up. And so the amount of energy in the heat there will be exactly the same as the amount of kinetic energy, which was exactly the same as the amount of gravitational potential energy at the top, which was the same as the amount of energy put into lifting the car in the first place. Okay, quick example here for the energy topic. They do like to talk about cost effectiveness and comparing the cost effectiveness of two appliances. Now, as it says up here, imagine you're asked to compare the cost effectiveness of two different types of appliance. They could be bulbs or fridges. Now, I've made up these two types of bulbs in this data here, but if we were to consider the cost effectiveness of them, you've got to, so for example, typical question, compare the cost effectiveness of the two bulbs over a 10-year period. I've got to consider how much does one bulb cost. Let's just look at this Solaro one. I need to work out the entire price of buying enough bulbs over that period. So each bulb lasts 1 year. I've got 10 years to go. And the running costs. Now the running costs per year, £2.50 per year, but I've got 10 years. Now, my cost to buy, I'm going to buy £1.50. I'm going to spend £1.50 each year. So again, I've got to times that by 10. Now, with my Luxmore bulb, well, they last 2 years. So how many am I going to need to buy if I want to compare them over a 10-year period? If each one lasts 2 years, I'm going to times that by 5. Now, my running costs per year is going to cost me 50p each year for 10 years. So my 50p is times by 10. Okay, just be thinking to yourself, how can I add up the total cost of buying enough of them and the running costs each year? Okay, so as an example, the cost for Solaro would be the cost of the bulbs plus the running cost for a year. And so like I did my sums up there, so my £1.50 times 10 lots plus my running costs, £2.50 for 10 years, adds up to £40. I'll do exactly the same for my Luxmore bulbs. This time, because each one lasts 2 years, I'm just going to times them by 5 lots, meaning my Luxmore, much cheaper over a 10-year period, so I can say that my Luxmore bulbs are more cost effective. Okay, mains electricity. You'll have seen this from the paper 1 video that I've recorded before. Just a few key things here. 230 volts is the mains electricity coming in through our plug sockets. A frequency of 50 hertz, and here's a plug that we've drawn from the back, and we can see that our neutral wire is blue meaning it goes on the left because of our second letter, brown goes on the right because of the second letter, and earth wire at the top there is striped, second letter being T for top. So example question, an engineer is fixing a plug socket. He has switched the switch to the off position. So by plug socket, I mean one of these on the wall, where you get one of those, one of those, one of those. So he's taken the cover off. He's turned the switch to the off position. Explain how the electrician can still get a shock. Well, the clue is in this part here. Yes, he's disconnected. He's disconnected the live from the neutral, so that if you plugged anything into it, it wouldn't turn on. But there's still a live wire in there, and that live wire has still got a voltage of 230 volts. So let's have a look at an answer relating to that then. So there's still got a large potential difference in the live wire. The man will provide a path for the current to go to ground. He's got a potential difference of 0, so there's a difference in the potential difference, difference in the voltage between him and the wire. So the current will flow through him, giving him a shock. Now, if I had to highlight elements that were particularly important, talking about current flowing through him, giving him a shock, there being a large potential difference still. Okay, now this would probably be my top tip of a question that I do think will come up in the paper, because of what I'm about to show you on the next slide. So this is Rutherford and Marsden's scattering experiment. This was what they replaced the plum pudding model with. The plum pudding model is that there were electrons scattered randomly inside a ball of positive charge. That's the old model, and they replaced it because of this experiment. So the experiment is, you get some alpha particles which are 2 protons, 2 neutrons joined together, same as a helium nucleus. So they were fired at a thin layer of gold leaf. There's a really thin layer, you can see the atoms there, only just 2 or 3 atoms thick. They fired them through, fired the alpha particles through, and they recorded where they went. Okay, now here were the results of the experiment. The results were 3 things. Most of the alpha particles passed straight through. Some deflected a little bit, they changed direction just a little bit. Very few, tiny number, deflected straight back to the source. So this one here that's hitting one on the nose and coming back again. So what does that tell us about the new model of the atom then? Because these results couldn't be explained with the old model. So it tells us that the atom is mostly empty space. Most of them go straight through, so it's got to be mostly empty space. Some deflected a little bit. Now, alpha particles are made of 2 protons and 2 neutrons. So 2 protons and 2 neutrons. Now, protons have got a positive charge. So overall, and neutrons have got a 0 charge. So overall, the alpha particles are positively charged. Now, in order to get deflected a little bit, it has to be because the nucleus is positively charged. Now, the idea that only a very few deflected back to the source, a tiny number came back to the start, tells us that the nucleus is small. If the nucleus was big, lots of them would have come back to the source. But the nucleus is small, hence only a tiny number came back. And therefore, that means the mass of the nucleus, the mass of the atom, is concentrated. The atom is huge compared to where all the mass is, which is tiny in the nucleus. And the ratio of the atom to the nucleus, for those people who remember these, is 1/10,000. So the size of the nucleus compared to the whole atom is 1/10,000. Okay, now the reason why I think that that's going to come up in the paper is because of this bit. Now, normally in the old course, this table here would appear somewhere in the chemistry papers, but it hasn't appeared yet, and I don't think it will come up in the chemistry paper too. So I think it's going to come up in this physics paper. So the idea that our nuclear model has a small concentrated positively charged nucleus, the negatively charged electrons orbiting in shells or energy levels. So this is our nuclear model we're really familiar with. Now, protons are positive, neutrons are neutral, okay, almost the same word. Protons are positive, neutrons are neutral, meaning electrons are the other one, so they're negative. Okay, now where is the mass in the atom? Well, the mass in the atom is in the nucleus, so that is why our two objects which are in the nucleus are the ones with mass. Now you can say 0 mass for the electron, or you can say very small. It does have a little mass, so very small is probably a better thing to say. Okay, now when using a symbol off the periodic table, when using an element symbol, we've got hydrogen here, an isotope of hydrogen. We've got the mass number, the massive number, the bigger number of the two, so we call it massive because it tells us the mass number of it, which is the number of protons and neutrons in the middle. Remembering our mass is found in the nucleus, so that massive number tells us the number of particles in the middle, so protons and neutrons. Now the atomic number is just the number of protons, which also happens to be the same as the number of electrons. So for all atoms on the periodic table, they've got the same number of protons and electrons. Now where this might come in with physics is they might ask you to explain the differences between these isotopes. Now an isotope has got a different number of neutrons. So same number of protons, that's the number down the bottom there. So all of these have got 3 protons, but in the middle they've got 6 protons and neutrons, 7 protons and neutrons, or 8 protons and neutrons. So this mass number tells us that there are different numbers of neutrons there. Now I've just remembered, I'm going to try and answer some questions off of the wall. If any of you have got any, please do continue to just put any questions up on the wall, and thank you for those people that have already posted. Okay, that is actually going to be the end of our Combined Science Foundation. So 55 minutes if you are a Combined Science on Foundation. Thank you very much for listening. And rest assured, you guys are going to have an advantage over anyone that hasn't watched this, which is about 100,000 pupils up and down the country. So you should be really proud of yourselves for putting in this time the night before. And thank you very much for listening, and well done. So I'm going to now go through some of the combined higher tier stuff, and you'll be pleased to see that there's only 2 things that come up on the higher tier paper that couldn't also come up on the foundation as well. So let's have a quick look at these then. So students should be able to describe ways to increase the efficiency of an intended energy transfer. So to increase the efficiency of a machine, what do we need to do? Well, adding oil is going to be a good idea. If we add oil, we're smoothing out the bumpy parts. We're going to be reducing friction, and friction causes energy to be wasted as heat. So adding oil to moving parts reduces friction, reduces wasted energy. If you've got a machine which is a heater or transfers heat energy in some way, having thermal insulation somewhere may well be the way to make it more efficient. So this is a water heater in here, a huge industrial water heater. It's covered in wool. Well, what's that going to do? It's going to reduce the energy lost to the surroundings as heat, so that I can keep this water at a high temperature. But the more insulation I put around it, the less energy is wasted. So I'm making it more efficient. Okay, now students should be able to calculate the net decline expressed as a ratio in a radioactive emission after a given number of half-lives. So what's that all about then? Okay, well, half-life is the idea that it's an amount of time it takes for the radioactive emission to go down by half. You may well have been used to seeing a graph of emission or radioactive atoms versus time. And chances are you would have been shown a graph that looks a bit like this. And to calculate the half-life from a graph, there's your top reading, what in this case 240. You go down by half to 120. You go across to the line. You go down to the time. That number there will give you your half-life. Okay, so half-life is the amount of time it takes for the radioactive emissions to go down by half. So if we just have a look at how the numbers might reduce each half-life. So let's say for argument's sake that the half-life of this is 200 years. So at the very start, I'm saying I've got 240 counts per second or emissions per second being given out by this radioactive lump of uranium. After one half-life, so after 200 years, it's gone down by a half. It's now at 120 CPS. After another half-life, another 200 years, it's gone down again to 60. After one more half-life, it's going to go down by half again, down to 30, and then 15, and then so on. Okay, now, if we had to express this as a percentage compared to the start, well, at the start, we start off with 240 CPS, so we can say that 0% has decayed, or we could say still, like how many, how shall I word that? I'm going to get rid of that bit. I'll just stick to the decayed idea. So after one half-life, we've got 120 left. So we can say 50% is decayed. Next, we've got, we're down to 60 emissions per second. Now we can say that of how many have decayed, if we have a look down here, so of our 240, 180 have decayed. So 180 over 240 times 100 gives us 75%. So 75% will have decayed. Now, when looking at after 3 half-lives, well, I've got my my number will now be down to 30. And if I've had 30 decay, I've got 210 left. So 210 left out of 240. Sorry, have decayed, rather, 210 have decayed. I'm now down to 87.5%. Okay, so you'd be looking at the percentage of how many have decayed, or equally, you could be looking at the percentage of how many you've got left. So at the start, you've got 100% of your atoms are all there ready to decay. After one half-life, you've got 50% of them. After 2 half-lives, where you've still got 25% left, you've got then 12.5% left. And all I'm really doing is I'm making these numbers go down by half each time, just the same as I do with my count rate. Okay, here's an example of a looking at the ratio of the number of daughter atoms compared to the number of parent atoms. So this scale down here is ND, so that's the number of particles which have decayed, and NP, which is the number of which haven't decayed yet. So we say parent and daughter. So you can see in this graph here that at the very start, at 0 half-lives, well, we haven't had anything decay yet, so our ratio is 0. Now, after 1 half-life, we're at a ratio of 0.5, or a decimal of 0.5, meaning that half of our parent atoms have decayed into daughter atoms. After 2 half-lives, we're going to be at 0.75. 3 half-lives, we're going to be at 87.5. Okay, so we can see here that as the half-lives go by along the bottom, the ratio of our daughter to parent is increasing. Now, eventually, when every single one is decayed, we would have a ratio of 1. That the number of daughter cells compared to the number of parent cells would be the same. If we started off with 240, let's say, atoms, and ended up with all of those decaying, we would have a ratio of 1. Okay, so the key things there really are to just look really carefully at what the labels say, because that's going to tell you the story of what the graph is. Okay. Okay, separate science only bit. So now, again, thank you anyone who is combined science. Thank you very much for listening. Enjoy the rest of the evening. Make sure you eat well and sleep well, and I'll see you tomorrow afternoon. Now, for the separate science only, let's just quickly go through a few bits of content then. As they're separate science only, it would make sense that these are going to come up in the exam, so I should be able to get through these in about 10 minutes or so. Okay, there is the idea in gas pressure that pressure times volume is a constant for a closed system. So what I mean by that is, here's a system of some particles in a box. If I do the pressure times the volume in this situation, and I now change the pressure because I've squeezed it, pressure times volume here would be equal to the pressure times the volume here. So for the same gas in 2 different situations, my pressure times volume equals my pressure times volume in the second situation. Now, if I do work on a gas, so what I mean by that is, for example, pumping it up, doing work on a gas increases the internal energy of the gas, and it can cause an increase in the temperature of the gas. So what happens there then? Okay, when you apply a force to a gas, so I'm compressing it or squashing it, you're doing work on the gas. Now, if you really wanted to, you could fill up a bike tire and you could squeeze it for about an hour, squeeze it and let go, and squeeze it and let go, and squeeze it and let go. And after about an hour, it will have warmed up a little bit, about a degree. So it really does work. Now, if you want to do it quickly, use a bicycle pump, because that's going to be applying a lot of force. It's going to be compressing the gas really quickly. So you can actually feel the end of the bicycle pump get hot as a result. So when you apply a force to a gas, you're doing work on the gas. And remember that work done is the same as the energy transferred to the gas. So by compressing a gas, like when you force it through a bicycle pump, you're transferring energy into the gas. So where does that energy go? The energy increases the internal energy of the gas, which basically means the kinetic potential energy of the particles. So by doing work on a gas, I'm transferring energy into the gas, which basically means it makes the particles move faster. It increases their kinetic energy. It increases their temperature. So if I had an exam question about explaining the effect of how a bicycle pump increases the temperature of a gas, how would I explain it? Well, when you apply force to a gas, you're doing work. The work done by the pump is the energy transferred to the internal energy of the gas. The kinetic energy of the particles will increase, so the temperature increases. Okay, so that's why the end of a pump gets hot. If you've ever slept on a blow-up bed as well camping, when you first blow it up, the gas is hot, and as it cools down, the bed deflates a little bit. So most people think that their air bed goes down on the first time they use it. Okay, electric charge then. So electric charge from an isolated sphere. What we really mean by this is like the Van de Graaff generator. This could be the top of the Van de Graaff generator, and if the Van de Graaff had a positive electric charge on the outside of it, we could draw the field lines always going away from the plus and going towards a minus. Now, if this was a Van de Graaff generator covered in negative electrons, we would see our field lines going in towards it. Now, the closer the lines are, the stronger the field. So that is why the field is really strong just around the Van de Graaff and gets weaker away from it. And the lines always go plus to minus. Just like magnets go north to south, field lines on electricity goes plus to minus, which is nice and convenient because that's the same way that current goes from a battery. It goes plus to minus as well. So if we had to I thought I'd just show these just in case this comes up in the exam, drawing field lines of two similarly charged objects. If they're both negatively charged, the field lines will push each other apart. And if they're opposite charges, the field lines will go straight to one to the other. This is the force of attraction that they're feeling. The arrow shows you the direction of the force they feel. The closer the lines, the stronger the force they feel. Okay, how do we charge up a rod with static electricity? Well, it's friction. So friction causes electrons to be transferred from one. When you transfer them from one, that'll become here we go. That will become positive to another, which will become negative. So it's only electrons that move. When they leave one place, you leave pluses behind, and they'll go to one, they'll be covered with negatives. Okay, so what is a spark then? So sparking is something to do with static electricity. It occurs when you've got a big enough difference between the number of electrons and the positive charges left behind. So when there's a big enough difference, so the potential difference is large enough, a strong electric field, these things here, a strong electric field strips electrons from the air. So the air molecules have electrons removed from them. This causes a current to flow. So that blue light there is the light given off by electrons being stripped from atoms, which is pretty cool. Okay, this is the required practical I went through at the start. Again, measuring the rate of heat loss for different insulating materials. Wrap each container in different materials. Take your temperature every 30 seconds. You're going to find that there is a steeper gradient at the start. Temperature comes down faster at the beginning than at the end because there's a bigger temperature difference at the start. Now, just a few notes about that, about heat transfer. Shiny silver stops radiation. Conduction and convection are stopped by trapped air. Reduced by trapped air. And conduction and convection are completely stopped by a vacuum. So this might be a drinks container here with a vacuum layer. That's going to stop your conduction and convection because there's no particles there. Okay, background radiation, a separate science-only topic. Background radiation, there is always a small amount of background radiation around us. So we're talking alpha, beta, gamma radiation. Realistically, it's gamma radiation because alpha and beta don't go very far. Now, most of it is actually from natural causes. Only a small proportion of it is from man-made. And of that which is man-made, nearly all of it is medical, as you can see here. So artificial sources is us, and medical is the biggest use of that. So nuclear power and weapons actually a really small amount. Now, professions which are a bit more at risk are our astronauts and air flight attendants and pilots, because they're up in the sky. And you can see here that a lot of our background radiation comes from cosmic rays from outer space. Now, people living in certain places in the UK have more background radiation because of a gas that comes out of rocks called granite. Now, in the last few minutes, feel free to just post any last questions up on the board, up on the wall again there. Now, so the background reading, because there is background radiation all around us, we have to subtract this background reading from any readings we're taking of an object. So if I want to find out if I've got some strange green slime on the beach that I found is actually radioactive or not, I've got to first take the background reading and subtract that from my reading of my green slime. Okay, fission and fusion then, one of our last topics. Fission is used to heat water in power stations. So that's a nuclear power plant uses fission. It does that instead of burning fossil fuels, and it will use fission of uranium or plutonium. Now, what exactly is fission then? So fission is where you have a large target nucleus, uranium or plutonium. You fire a neutron into it. That neutron makes it unstable. It's going to decay. It's going to release more neutrons, and it's then going to release two fission products. It's going to release two smaller nuclei. So it's a large unstable nucleus, receives a neutron and splits into two smaller nuclei. Now, I can't make it more important, important enough to say you've got to say nucleus. You can't say atoms. Even if you give a lovely description, if you say atoms, you get no marks. So energy comes out and more neutrons. Those more neutrons go on to cause a chain reaction. Okay, fusion then, fusion occurs in stars, and it's how all the elements in the universe are made. So inside stars, small nuclei fuse together. Again, it has to be nuclei. They fuse together to make a larger nuclei, releasing lots of energy in the process. And it's that energy that comes out of the star that warms up our planet. So fusion is really important in stars. Fission is really important in power stations. Fission is splitting. Fusion is joining of small elements. Now, just before we go, I would like to just leave everyone with a parting message.